Uh, okay, so let's start this session. Uh, as most of you know, Professor Yeung is Claude Shannon awardee for this year. All of us who have known Raymond and have association with Institute of Network Coding and CUHK, this is a very, very special news to celebrate. Uh, I can imagine that this must be the busiest year for Professor Yeung so far, and yet he has given us this his invaluable time to us. I cannot thank him enough for this. On a personal note, I like to say that the work by Professor Yeung has had profound impact on me and has motivated me and given me directions to work in this beautiful field of information theory. Also, from an academic genealogy point of view, he is my grandfather. Through my PhD advisor, Professor Terence Chen, whose PhD guide was Raymond himself. So young students and many of us are getting this unique opportunity to learn directly from Professor Yeung, and I encourage each one of you to make the most out of this learning experience. Professor Bikash Kumar Day is our chairing this session. Professor Bikash Kumar Day is a faculty member at IIT Bombay. He has made important contributions to information theory and network coding through his research and academic educational activities. Again, we are fortunate that Professor Bikash Kumar Day will be chairing sessions for Professor Raymond Yeung for today as well as tomorrow. Thank you, both of you, and I hand over to Bikash now. Thank you.
Hello, everyone. First of all, let me say that again, thank Professor Raymond Yeung for agreeing to give this tedious series of lectures, and it's a very beneficial thing for the students to learn some of the basic information theory as well as a little bit of network coding from the horse's mouth, so to say. And to talk about accomplishments of Raymond, one always finds a loss for words. I'll try to give a glimpse of his accomplishments. So Professor Raymond Yeung did his PhD from Cornell University, after which he spent a few years at AT&T Bell Labs. And after that, for over 30 years, he has been in Chinese University of Hong Kong. So he has been teaching there and working on information theory, network coding. And he has given one of the first, the first information theory MOOC on Coursera, which has been seen widely by students. And he has been in the Board of Governors of IEEE Information Theory Society. He has been in various roles in many conferences and journals. He was an associate editor for IEEE Transactions on Information Theory. He is currently in the editorial board of the special areas of Information Theory Journal of Information Theory Society. And he is in the editorial board of 2 journals of Foundations and Trends on networks and information theory. And the most important thing, of course, is which you already know now, that he is a Shannon Award winner, most recent Shannon Award winner. And in fact, he's the winner of the 2 topmost awards of the Information Theory Society, the Hamming Award and Shannon Award. And having said this, nothing else needs to be said about research accomplishments of Professor Raymond Yeung. But most important thing that some of us who have worked on network coding, that we know Raymond as the founder of the network coding as a field. He was a co-author of the first network coding paper titled Network Information Flow in 2000, which started this field of network coding, which has afterwards seen tremendous activity, and it started the whole field of network coding. He has also established Institute of Network Coding in Hong Kong, which has supported many researchers to do research in information theory and network coding. And this way, he has helped many researchers to work in this area. So I think with this, I'll keep it short. I can hardly do justice to all the accomplishments of Raymond, but I think to better things, I'll let Raymond start. Thank you, Raymond, again.
Okay, thank you. Thank you so much for the kind introduction and also for the invitation. It's really my great pleasure to be here. Oh, by the way, my background is as a picture from my university. I will invite all of you to visit sometime. Okay, let me start by sharing the screen. So can you see now? Okay, good. Let me see. I think I should. I think that's fine. Okay, now there was some echo just a moment ago. Now seems to be okay. Can you hear me properly?
Yes, we can hear.
Okay, very good. So there will be two parts in today's lecture. The first part is on the information measures, and the second part is on typical sequences. So this lecture is actually pretty much based on my own textbook on information theory. So you see the numbering of the sections and things like that. Okay. So if you want to, let me see. Request the live description be enabled for the meeting. Okay. So if you want to make reference to the specific theorems or lemmas, you can do so by looking up my book. All right, so let me start. So this is the book I published in 2008, which is the kind of like the second edition of my previous book. Okay, so let me start by introducing Shannon's information measures. The first one is entropy, with the second one is conditional entropy, which is just a conditional version of entropy. And then we have a mutual information, and then the conditional version of it. Okay, so first we have this definition for the entropy of a random variable x denoted by h of x, which is given by the negative of the summation overall x. I'm going to explain a little bit regarding this summation. Px is the probability of the occurrence of a value small x of the random variable capital X, and then log of the probability. Now here we're going to use the convention that the summation is taken over the support, which means that whenever the probability of 0, we don't include it in the summation. And the base of the logarithm is just some arbitrary positive numbers. Arbitrary positive number. Usually we take it as 2, but it can be any positive number alpha. And when we take the logarithm to in the base of alpha, we write this as h sub alpha of x. If we want to specify the base. Now, entropy, as we are going to see, measures the uncertainty of a discrete random variable. Okay, this is a very high-level description of a very important property of entropy, which we will explain in great details later. And the unit of entropy is usually called a bit. If alpha is equal to 2, it's called net. If alpha is equal to E, if alpha is equal to D, I gave it the name dit, okay? Although it's not very commonly used terminology. Now, I would like to point out that a bit in information theory is different from a bit in computer science, because you see immediately from the definition of entropy that has something to do with probability. Okay, and whereas in computer science, a bit is just a quantity which can take the value 0 and 1. It's nothing to do with probability at all. Okay? Whereas in information theory, a bit is a unit of information, meaning that we're trying to use it to measure the uncertainty contained in a random variable. Now, another remark I would like to make is that the entropy of a random variable x depends only on the distribution of x, namely p of x, but not on the actual values taken by the random variable. Okay, and what it means is that the alphabet can be ABC, or the alphabet can be 0, 1, 2. It doesn't matter. Okay, it only depends on the probability, and therefore sometimes we also write it as the entropy of the distribution p of x. Now, here I mentioned that in this context we I'm sorry about that the renovation happening. So I hope it is bearable. So the convention here is that the summation, whenever we talk about summation in this lecture, we sum over the support of x. Okay. If we take the expectation of a function g of x, where x is the random variable that we're talking about, summation px gx is a summation over all x such that x is in the support of the distribution. Okay. Now we know from basic probability theory that the expectation operator is linear, namely that expectation of f of x plus g of x is equal to expectation of f of x plus expectation of g of x. Okay. Now there's some subtlety here, because here we are taking the convention that the summation is taken over the support. Okay. With this small deviation, linearity of the expectation operator continues to hold. Okay. So there's some minor details here which I won't explain here. If you're interested, you can refer to problem 5 in the textbook for chapter 2. Okay, so now with this expectation operator, we can write the entropy of x as as minus the expectation of log of p of capital X. Okay, where p of capital X is the probability of the random variable. So by itself, it is also a random variable, and using this notation, we can expand it into the minus summation x px log px as before. Okay, so next thing I would like to introduce is the binary entropy function, which is the entropy in the case that there are only two possibilities. Now, the binary function with parameter gamma, where gamma is between 0 and 1, is defined as follows. So entropy, binary entropy with parameter gamma is equal to minus gamma log gamma minus 1 minus gamma log 1 minus gamma. With the convention 0 log 0 equals 0, okay, because in the case that gamma is equal to 0, then the gamma log gamma becomes 0 log 0, which is undefined. But we adopt the convention that it is equal to 0, and this is justified by L'Hopital's rule, because when you take the limit of a log a when a tends to 0, it is equal to 0. Okay, so this is the appearance of gamma in the expression. Okay. So evidently, if we have a binary random variable which takes two values with one probability being gamma, the other probability being 1 minus gamma, the entropy of this random variable x is equal to the binary entropy function evaluated at gamma. Okay. Okay, so this is the plot of the binary entropy function, where gamma is between 0 and 1, and it is a concave function with when gamma is equal to 0, it takes the value 0. When gamma is equal to 0.5, it takes the maximum value equal to 1. When gamma is equal to 1, it becomes 0 again. So it is actually symmetrical around gamma equals 0.5. You see that the binary entropy function is maximized when gamma is equal to 0.5, which means that it is a uniform distribution on a binary alphabet. Okay, and this is the case when the information contained in the random variable is maximal. Okay, now in addition to defining the entropy of one random variable, we can also define the joint entropy of a pair of random variables x and y, which is given by this formula. Entropy of x, y is equal to minus summation x, y, pxy log px comma y, which is in terms of the expectation notation can be written as minus expectation of log of the probability of the joint of the pair of random variables. Okay, now this is this summation summation pxy over all xy actually corresponds to the expectation. Okay, so so just like what we do all the time, you know, when you take the expectation of this random variable, you just write out as the average over the probability, and then you replace capital X and Y by small x and y. Okay. Nothing more than that. Okay, so we also have the conditional entropy of a random variable y given a random variable x. Now this is given as the entropy of y given x. Okay, written as the entropy of y given x, and is let me go back. Okay, it is let me just look at here. Okay, it is equal to minus expectation of log of py given x. This is actually what I would like you to remember, okay, instead of remembering this this complicated summation. So the way you remember is that, you know, if I remove the conditioning, this becomes entropy of y equals minus expectation of log of p of y. It's just the regular definition of entropy of y. But then if you remove this, I'm sorry. Okay. So and then if you do a conditioning on the entropy, and then you do a conditioning on the expectation, then you obtain the correct formula for entropy of y given x. Okay, so now so we write entropy of y given x equals minus summation xy pxy log py given x. Okay, now and then we write py, we write pxy as px times py given x. Okay, and then for summation x comma y, we split it into two summations. Now with this, we can fish out a px and then move it outside, and then the inside the square bracket we have minus summation y py given x log py given x. Okay, now the inner sum is should be interpreted as entropy of y conditioning on a particular small x. Okay, and so you see that if we remove the conditioning, it just becomes the regular entropy of the random variable y. But now by conditioning on both py, okay, then you you get something which we would denote as entropy of y given x equals a particular small x. Okay. So with this notation, we can write this line, the line at the bottom. Entropy of y given x is equal to summation x px times entropy of y given x equals a particular x. So you see that's the entropy of y given a random variable x is just the entropy of y given a particular value of the x value, and then you average it over the average out using the px as the weighting function. Or you can think of it as a convex combination. Okay. All right. Similarly, if we condition on two random variables, entropy of y given x and z, the two random variables x and z, we can write this as summation zpz. Okay, the probability of small z, entropy of y given x comma, and then z takes that particular value small z. Okay. Okay, where entropy of y given x comma z equals small z is given by this expression as we expect. Okay, so this is equal to this. Okay, again, the way to understand this conditional entropy function, conditional entropy by conditioning on particular value of z, is that if you remove the z throughout the equation, then you find that entropy of y given x is equal to minus summation x comma y pxy log of py given x. Okay, so this is just the regular formula for entropy of y given and a random variable x. Okay, but then you now condition on a particular value z throughout. Okay, and then you'll get the right answer. Okay, now here are two very simple propositions. The first one says that the joint entropy of x and y is equal to entropy of x plus entropy of y given x. And the second one is very similar to the first equation, except that you exchange the rows of x and y. Okay, and then you get entropy of x, y equals entropy of y plus entropy of x given y. So this very basic relation tells you that you can actually write the joint entropy as the entropy of one random variable plus entropy of the other random variable conditioning on the first random variable. So if you think of this as uncertainty, what it is saying is that the uncertainty of the pair of random variables x and y is equal to the uncertainty of the first random variable. Okay, now I tell you the first random variable, I remove that uncertainty. And then the remaining uncertainty is the conditional entropy of y given x. Okay, the proof is actually quite simple. It is very convenient to prove it by using the expectation operator, namely that entropy of x, y is equal to minus expectation of log of p of x comma y, the pair of random variables. And now for the p of x, y, we can write this as px times py given x. Okay? And then the log of the product is equal to the summation of the log. So we have minus expectation of log of px minus expectation of log of p of y given x, where the first expectation is simply equal to entropy of x, and the second expectation is simply equal to entropy of y given x. So this proves the first formula, and the second formula can be proved likewise by exchanging the rows of x and y. Okay, so now we introduce another quantity called mutual information between x and y. So we have two random variables x and y to start with. The mutual information is given by this. This is equal to expectation of log of the joint probability, joint distribution divided by the product of the marginal distributions. Okay. So you can write down the summation as usual. Now again, this the summation pxy corresponds to the expectation, and then the inside the summation we have a log of pxy divided by pxy, and then in the expectation operator you just replace the small x by capital X and small y by capital Y as usual. Now, the one thing I would like to note is that the mutual information is symmetrical in X and Y, which is evident from this expression here, because this expression is symmetrical in X and Y, evidently. Now, in the literature, it is also written in a somewhat different form, namely that by writing px comma y divided by py as px given y, okay, we can write this summation as the expectation of log of px given y divided by px. Okay. Now, usually I don't prefer this this expression for mutual information because it's not apparent from this form that IXY is in fact symmetrical in X and Y. Okay. Although it is symmetrical, but it's not very obvious if you write in this form. Okay. Now a very important interpretation of the mutual information is that when you talk about the mutual information between a random variable x and itself, that is, you let x equals y, then the mutual information reduces to the entropy of x. Okay, now we start with, to see this is the case, we start with the definition of IXY. And now P, when x is equal to y, then the IX semicolon x becomes expectation of log of px comma x divided by px times px. Okay, and but px comma x is just equal to px, and with this we can eliminate the px upstairs and downstairs, and this becomes minus log of px, and this reduces to entropy of x. So we have proved this formula, and so for this reason, the entropy of x is sometimes called the self information of x. And some people like to use this interpretation. Now, the next proposition is also a very basic relation between different information quantities. This proposition says that the mutual information between x and y is equal to the entropy of x minus the conditional entropy of x given y. Okay. Now, another way to apply the same result is that IXY is equal to entropy of y minus entropy of y given x. Now, this is immediate from the first line because you see that the mutual information on the left-hand side is symmetrical in x and y, so you can exchange the rows of x and y and obtain these two formula, the second formula accordingly from the first formula. Now, another formula is that the mutual information between x and y can be written as the entropy of x plus entropy of y minus the joint entropy of x and y. Now, provided that all the entropies and conditional entropies are finite, because if some of these quantities are not finite, then you may run into infinity minus infinity, that kind of situation. So we will exclude these situations when we write these formulas. Now, these formulas are rather simple, and they can be proved using some very elementary techniques, which I won't talk about here. But I would like to remark that for example, this formula, okay, which is taken from here, is analogous to a set theoretic identity, okay, mu A intersect B equals mu A plus mu B minus mu A union B. Okay, this is just the a variation of the inclusive exclusive formula. Okay, so here you see that the X corresponds to a set A, Y corresponds to a set B. The semicolon corresponds to the set to the intersection of sets, and the here the entropy of X comma Y corresponds to mu of A union B. Okay, so the comma corresponds to the union, and where mu is just any set additive function, and A and B are sets. Okay, so this because of this one-to-one correspondence, we actually can visualize the relation of these information measures captured by the previous few propositions in terms of something called an information diagram. Okay, in this diagram, we regard the circle on the left-hand side as the entropy of X, the circle on the right-hand side as the entropy of Y, and the union of the two sets being the joint entropy of X and Y, and the value taken by this atom, or the weight of this atom corresponds to entropy of X given Y, and this corresponds to entropy of Y given X, and the intersection corresponds to the mutual information. Okay. Now there's a theory behind this analogy, but I'm not going to cover this in this course, but I'll just give you some highlight of what these information diagram can do. Okay, this is the information diagram for 3 random variables, and the analogy prevails. Now, in this information diagram, I would like to point out that the weight of each atom in the information diagram, which we denote by mu star. Mu star is actually it's a specific set theoretic function, not just any set theoretic function. Okay? Corresponds to a Shannon's information measures, except for the intersection of 3 sets. Okay, to see this, for these 3 atoms, they're in the form of conditional entropy, which is always non-negative. Okay, and for these 3 atoms, they are in the form of conditional mutual information, which are also non-negative. Now, however, the intersection of the 3 sets does not seem to correspond to any familiar information measures, and in fact, this this quantity, which I took liberty to denote by ix1 comma semicolon x2 semicolon x3, okay, actually can take a negative value. Okay, so let's be very careful about this when we use the information diagram. We have to keep in mind that certain atoms can take negative values. Okay, so this is a very basic example showing that the quantity in the middle can become negative. Okay, so this is a situation when x1 and x2 are fair bits, meaning that they're IID and uniformly distributed on 0 and 1, and x3 is simply the modular 2 addition of x1 and x2. Okay, in this case, we see that the information diagram actually looks like this. Okay, with the intersection of the 3 parts of the 3 sets being negative. Okay, now for 3 random variables x, y, and z, the mutual information between x and y conditioning on z is defined like this. Again, I would like to draw your attention to the expectation expression. Okay, in this if you look at the left-hand side and the right-hand side. Okay, if you strike out the conditioning on z, then it reduces to the usual definition of the mutual information between x and y, and then you condition on z throughout, and then you get the right formula. Okay, again, I would like to point out that the mutual information between x, y given z is symmetrical in x and y, as you can see from this this expression here. And similar to entropy, we can also write ixy conditional on z equals summation x px, the mutual information between x and y conditioning on a particular z, okay? Where the this conditional mutual information on conditioning on particular z is given by this formula. Okay? So I think I would like you to pay attention to this without getting into the details. Okay, again, in this formula, if you strike out all the conditioning on z's, then it reduces to the usual formula for mutual information between x and y. Okay, again, just like the unconditional version of entropy, the mutual information between a random variable x and itself conditioning on another random variable z is equal to the conditional entropy of z given z, or conditional entropy of x given z. That is, ix given z is equal to entropy of x given z. Again, if you strike out the conditioning on z, then it reduces to the previous result that we have seen. Okay, and then we have conditional versions of the formulas that we have obtained before. If you strike out the condition on z, then it reduces to the previous formulas. So you see that well, it is actually true that whenever you see an identity of information quantities by conditioning on another random variable throughout the formula, then it continues to be a valid formula. I'm not going to give a formal proof on this, but I just want to point out that this is the case. Okay, now another remark which is quite important is that all Shannon's information measures are actually special cases of conditional mutual information. So in other words, conditional mutual information is the most general form of Shannon's information measures. Now to see this, we let phi denote a random variable that takes a constant value, or it's like a dummy variable. Then we have the entropy is equal to the mutual information of x and itself conditioning on a dummy variable. And then entropy of x given z is just mutual information between x and x conditioning on z. And unconditional mutual information between x and z is simply mutual information between x and z conditioning on this constant variable phi. Okay, so this brings me to the end of the first section. Let's see. Actually, I may be spending too much time. I think I need to go a little faster. Okay. All right, then we talk about the chain rules, which is section 2.4 in my textbook. Okay, the chain rule for entropy has this expression. The joint entropy of x1, x2 to xn is equal to summation of entropy of xi conditioning on x1, x2 up to xi minus 1. That's all the previous random variables. To give you some feeling, let's work it out for n equals 2. For n equals 2, it says that entropy of 1, 2 is equal to entropy of 1 plus entropy of 2 conditional on 1. This is a proposition 2.6 that we have seen before. And for the case when n equals 3, we have entropy of 1, 2, 3 equals entropy of 1 plus entropy of 2 conditional on 1 plus entropy of 3 conditional on 1 and 2. So with this, you can see the pattern. Okay, And then we also can have the condition, the chain rule for conditional entropy. Now here, if you, oops, I'm sorry. Here, what you do is just to condition everything on y, right? And then you by conditioning on y for every term in this formula, then you get another valid formula. Okay. We also have the chain rule for mutual information. Here we, on the left-hand side, we have the mutual information of n random variables and another random variable y. Then it is equal to this summation on the right-hand side. Again, let me give you some feeling of what it is. When n is equal to 2, we have mutual information of 1, 2 with y. Okay, is equal to mutual information of 1 and y plus mutual information of 2 and y conditioning on the first variable. And n is equal to 3. The mutual information of 1, 2, 3 and y is equal to entropy, mutual information of 1 and y plus 2 and y given 1 plus 3 and y given 1, 2. Okay, so again, you see the same pattern. And again, you can obtain the chain rule for conditional mutual information by conditioning on another random variable z throughout the whole formula. Now, so I'd like to give you a simple proof of the chain rule for conditional entropy. Maybe in the interest of time, I'll just skip this. If those of you who are interested, you can check out in my textbook or in any other textbooks. Okay. Okay, so it's actually a very short section. Okay, very quickly we go to another section, which is about something called informational divergence. Okay. Now, the informational divergence is defined between two probability distributions, P and Q, on a common alphabet, X. Okay, if they're not on a common alphabet, then we cannot define the informational divergence. Now, the informational divergence, denoted by this, is equal to summation X, Px log Px divided by Qx. Here, I color code the Px and Qx to help you to recognize the pattern. Okay, so this is the same Px, and this is an Qx is something different. Okay, or you can write this as the expectation of log of Px over Qx. Okay, where the expectation E sub P denotes the expectation with respect to the distribution P of X. Okay. Now, here the convention is that the summation is taken over the support of P, okay, because you're taking the expectation with respect to P of X, and we also adopt the convention that C log C over 0 is equal to infinity if C is greater than 0. Okay, because C over 0 we take as infinity, is log of infinity. Infinity is also infinity. Okay. Now, another observation is with these conventions, if the divergence of P and Q is finite, then whenever Px is greater than 0, okay, Px is greater than 0 here, okay, so that is included in the summation, then Qx cannot be equal to 0. Otherwise, one of the terms will blow up. Okay, and therefore, what we see is that whenever Px is greater than 0, Qx must also be greater than 0, and which means that the support of P is a subset of support of Q. Okay, if this is not the case, then the divergence can explode. Okay, so divergence of P and Q measures the distance between P and Q in some sense. In particular, when P is equal to Q, then the divergence is equal to 0. Okay, the distance between a distribution and itself has to be 0. However, now dpq is not symmetrical in P and Q, which means that it's not equal to dqp. So it is not exactly a true metric, and also it doesn't satisfy the triangular inequality. Okay, we have to keep this in mind. Okay, so the informational divergence is also called the relative entropy or the Kullback-Leibler distance in literature. Okay, here's so far we have been talking about identities, okay, and now I'm going to talk about the first inequality in information theory, which is a very important one. That's why it's called the fundamental inequality. So it states that for any a greater than 0, log a is less than or equal to a minus 1, with equality if and only if a is equal to 1. It's a very elementary inequality that everybody can prove using high school calculus. And this is what it says. Okay, so log a is less than a minus 1. Okay, so the straight line is a minus 1, and the curve is log a, and the curve and the straight line intersects at the point when a is equal to 1. That's all it says. Okay, it's very elementary, but it's extremely useful in information theory. Another variation of it is that if we substitute a by 1 over b, okay, then we obtain another inequality, or you can say that you replace a by 1 over a, then after some manipulation you get this. So this inequality says that log a is lower bounded by 1 minus 1 over a. Okay, so the fundamental inequality gives you an upper bound on log a in a linear form. Okay, and the second inequality gives you a lower bound not in a linear form, but in the reciprocal of a. Okay. So both of these forms of the fundamental inequalities are very useful. Okay, so let's skip this. And also, we know that in corollary 2.30, it says that this inequality is tight if and only if a is equal to 1. The reason being that you just replace a by 1 over a when it is tight. When a is equal to 1 for the fundamental inequality, then this inequality got to be tight when 1 over a is equal to 1, which again means that a is equal to 1. Okay, so here is another very important inequality called the divergence inequality. Okay, this may be the first non-trivial inequality in information theory. Now, this the divergence inequality says that for any two distribution, again they're defined on a common alphabet, the divergence P and Q is greater than or equal to 0 if equality, if and only if P is equal to Q. So in some sense, this quantifies the divergence as a distance, because conceptually a distance cannot be negative. Okay? And this says that the divergence is always non-negative. With equality, if and only if P is equal to Q, and this also makes sense from the intuitive point of view, because if it qualifies as a distance measure, then the distance between something and itself got to be 0. And this is actually it's also the necessary and sufficient condition. Okay, so now here's the divergence inequality. It's a straightforward application of the fundamental inequality, but there's a small complication, namely that when the P and Q don't have the same support, okay, then we have to do a little bit extra work for that. But let's for simplicity assume that the P and Q have the same support. Now then the proof is very simple. The dpq is equal to summation px log px, summation px log px over qx, and then now we change this logarithm to this logarithm can be in any base. We change it to the natural logarithm, and then that's why we have an extra term log e here. Okay, and so this becomes summation px natural log px over qx, and then we apply the second version of the fundamental inequality to lower bound this natural logarithm. Okay, so this is you regard this as a, right? So log a is greater than or equal to 1 minus 1 of a. So so px becomes downstairs and qx becomes upstairs, and then now px this cancel with this px, and so we get the first one is summation px times 1, which is summation px, and then the second one is summation qx. Okay, so now here, because we assume that they have the same support, okay, sp is equal to sq. So the first summation obviously is equal to 1 because summation px over its own support is equal to 1. For the second term, we can write this as sq because we assume that sp is equal to sq, okay? And therefore, it's now also evident that the second summation is equal to 1 because you're summing qx over the support of q, okay? So at the end, we get a log e1 minus 1, which is equal to 0. Okay, so that's the proof of the divergence inequality. Okay, so all right. Now for the equality to hold in 2, we have to check out this inequality here because this is the only step that involves an inequality. And here we apply the fundamental inequality, which is tight whenever px over qx is equal to 1, or px is equal to qx for all x in the support. Okay, so this means that the divergence inequality is tight even only if p is equal to q. Okay, now a variation of the divergence inequality is a very interesting inequality called log sum inequality. And I don't know who introduced this first. It is quite likely that Immatrice was the first one to use this inequality. And so it takes this form. For positive numbers, A1 and A2, so on and so forth, and non-negative numbers, B1, B2, so on and so forth. So the first set of numbers is positive, the second set of numbers are non-negative, okay? And such that if we sum up A is it is less than infinity, and if you sum up B, it is strictly positive and less than infinity. Okay, so some of these BIs may be 0, but when you take the summation, it must be some of them must be positive. Right? So then we have this very interesting inequality, which says that summation AI log AI is greater than or equal to summation AI log summation AI summation BI, right? So it's kind of like, you distribute the summation into each of these terms, right? And then you obtain a lower bound. Now and moreover, equality holds even only if AI equals BI divided by BI is equal to a constant. That is, they're proportional to each other. Now to get you some feeling of the log sum inequality, just write out for the case when you have 2 terms. Now, so the left-hand side becomes, A1 log A1 over B1 plus A2 log A2 over B2 greater than or equal to, you sum A1 and A2 together, okay, and the red and the blue comes together, okay, and then log of the red and the blue coming together, and then here the red and the blue are coming together, okay. So this is the pattern. This is what the log sum inequality says. Okay, so well, I mean, I'm going a little too fast. Just give you 2 more seconds to look at this formula. Okay, so if you have 3 terms, then things goes as you would expect. Okay, so now the divergence inequality implies a log sum inequality. The divergence inequality actually is is an application of the log sum inequality can be obtained as an application of the divergence inequality. Okay, you just normalize the AIs and BIs and make them into probability distributions. Okay, now but it turns out that the log sum inequality also implies the divergence inequality. Okay, so the two inequalities are actually equivalent. None of them is stronger than the other one. So I leave this as an exercise. Okay. So so very quickly, I also finished another section. Okay, so I think I'm running late. So let's see what we want to do with this. Okay, so the next section is on the basic inequality, and so there's only one result from in this section, namely that for three random variables x, y, and z, the mutual information between x and y given z is always non-negative. With equality, even only if x and y are independent when conditional on z. Okay. So so this implies all Shannon's information measures are non-negative, as we have pointed out. That's the conditional mutual information is actually the general form of Shannon's information measures. Okay, so here's a quick proof, because I want to correlate this with what we have learned in the last section. Now so we're going to prove that the mutual information between x and y conditioning on z is actually non-negative. It's always non-negative. Okay, so we write out this expression, and then we break the summation into two summations, namely summation on z and then summation x comma y. Okay, and in the next step, we write this as P of z, that the joint probability of x, y, and z as P probability of z times probability of x, y given z, log of the same thing. Right? We didn't change anything, and then we move the P of z outside the double summation, and now we see something very interesting inside the summation. The inner summation actually is the divergence between x and y conditioning on z. Okay, so this is a conditional joint distribution. Okay, and then log of this, the same thing, right? This and this are the same thing. And then downstairs we have the marginal marginal probability of x given z, and then the marginal probability of y given z. So literally, this summation is the divergence of pxy given z, the joint distribution of x and y conditioning on a particular z. And then downstairs we have the marginal distribution of x conditioning on a particular z, and then the marginal distribution of y conditioning on a particular z. Okay. Now okay, so we are almost there now, but we note that this is this is obviously a valid joint distribution, and the product marginal distribution is also a valid joint distribution on the product alphabet. Okay, therefore, by the previous theorem, we see that this divergence is actually non-negative. Okay, so and therefore the theorem is proved. So you see that the mutual information between x and y conditioning on z is indeed equal to average to this divergence by conditioning on z, and then you average overall of z with a distribution of z as the weighting function. So that's why we end up having that the conditional mutual information is always non-negative. Okay, now how about the equality condition? Now, in order for this to be exactly equal to 0, then the divergence need to be 0 for all z. Okay. Equivalently, this is the case whenever pxy conditional on z is equal to px conditional on z times py conditional on z, and this has to hold for every small z. In other words, we have this pxy given z is equal to px given z times py given z, or equivalently, x and y are independent conditionally on z. Okay, so this is how we get the equality condition. Okay. Okay, and then there are some simple propositions which I will just mention. First of all, in the entropy of x is equal to 0 if and only if x is deterministic. Okay, well, in general, entropy of x is non-negative, but in a case where that it is equal to 0, then x must be deterministic, meaning that there's only one probability mass, and there's which is equal to 1. All the rest are equal to 0. Okay, and then when conditional entropy of y given x is equal to 0, it means that when you're conditioning on x, then y is deterministic. Another way to say it is that y is a function of x. Okay. And when the mutual information between x and y is equal to 0, then the necessary and sufficient condition is x and y independent. Okay, just the special case of the previous theorem by conditioning on a constant variable. Okay, so we are done with this. Okay, so in this section, we're going to talk about some useful information inequalities. Okay, first one is conditioning does not increase entropy, meaning that the entropy of y when conditioned on x cannot be larger than entropy of y. So, intuitively, it means that if you're interested in y but now I know some psi information x. If I tell you that psi information x, then your uncertainty about y can only be reduced. So that's what this theorem says. And equality holds even only if x and y are independent, meaning that when these two quantities are the same, meaning that telling you x doesn't tell you anything about y, or equivalently, x and y are independent. Okay, the proof is just one line. Okay, this conditional entropy of y given x is equal to entropy of y minus the mutual information between x and y is less than or equal to entropy of y, because this is non-negative. Right? Now the equality constraint, equality holds even only if ixy is equal to 0 when x and y are independent. Okay, so I'm just trying to give, I'm not going to give you all the proofs, but I just want to give you some proof to correlate with what I just talked about. Okay, similarly, we have this, we have entropy of y given xz is less than or equal to entropy of y given z, because here we are conditioning on an extra variable x. So this is just a conditional version of this of the previous inequality by conditioning on extra z, right? So so if you remove this, then it becomes the previous theorem. Okay? Now, here is a warning. The mutual information of xy given z, if you remove the conditioning, it does not hold in general. Okay, conditioning does not increase entropy, but conditioning can increase mutual information. That's something you need to be careful about. Okay, and then we have this independence bound for entropy, which says that the joint entropy is always upper bounded by the summation of the individual entropies. Okay. Now I'll give you a quick proof. So we apply the chain rule for entropy. So here we have the joint entropy, and this is the chain rule. Okay? Chain rule takes the form of the summation. And then because conditioning does not increase entropy, this conditional entropy is upper bounded by entropy of xi. So this proves the independence bound already. Okay? And then for it says that the equality condition holds if and only if all these xi's are mutually independent. Okay. To figure this out, you only have to check out these inequalities, and maybe I'll just skip the details. So I just want to mention that the necessary and sufficient condition for the independence bound to be tight is that all the random variables are mutually independent of each other. Okay. Okay. Now another inequality which we use every so often is that now here on the right hand side is mutual information between x and y. On the left hand side we have mutual information between x and y plus an extra random variable. Okay, so this intuitively it is correct, because if you increase y from change y to y and z, which you enlarge the random variable, then the mutual information should also be enlarged. Okay, so let's skip this. Skip the proof. Okay, now the next lemma is something leading to the celebrated data processing theorem, which has the following. Which says the following: if we have a Markov chain x, y, z, then the mutual information between x and z, that is the mutual information between the two random variables on the side, is less than or equal to the mutual information between x and y. Because they're closer, okay, in terms of the geometry of the problem, because the x, y is closer than x and z, and therefore x and y, have a higher mutual information than x and z in general. Okay. Likewise, x and z, for the second line, the mutual information between x and z is less than or equal to the mutual information between y and z, because y and z are closer to each other on the Markov chain. Okay. So with this, I'm going to skip the proof. But one thing, the proof are elementary. But one thing I would like to mention is that here it leads to the celebrated data processing theorem in information theory, which says that if you have a linked 4 Markov chain with the variables x, u, x, y, and v, then the mutual information between u and v, okay, the two random variables at the two sides, is upper bounded by the mutual information of the two random variables in the middle. This is the celebrated data processing theorem. Okay, well, I'm not going to offer you a proof. I would like to offer you this picture. Okay. So previously we have seen the information diagrams for random variables. But it turns out that if the random variables form a Markov chain, okay, then the information diagram can be drawn in a very simple fashion, just like this. Okay. And you draw a mountain here, a mountain here, a mountain here, and a mountain here, and they overlap with each other. Okay? Now, it turns out that for this information diagram, you can easily fish out the following. So we are interested in IXT, which corresponds to the intersection. It's less than or equal to IYZ. Okay. IYZ is the intersection between Y and Z, and it contains these four atoms. Now, these 4 atoms are all each of them is equal to a Shannon's information, mutual information. That's why they are non-negative. And IXT, okay, is just one of these terms, and therefore, let me add. immediately we see that this inequality holds. Okay? This part is upbounded by this because all these three dots are non-negative. So with this, I'm finished with another section. So maybe I'll take a break. Okay, I'll take a break, 5-minute break, and then we'll come back and cover Farnell's inequality. Is that okay?
Yeah, sure.
Okay, all right, thank you. So I'll see you guys in 5 minutes.